This is Michael Obluda. I'm going to explain Archimedes' law first. And Archimedes' law states that if you put an object in water, the amount of water, the volume of water that it displaces, the weight force from that water is equal to the buoyant force on the object. And buoyant force is just the force pushing up from the water towards the surface on the object. And this is seen when like ice cubes float. They're the buoyant force is higher than the weight force of the ice cube sinking down, and this is because the buoyant force is equal to density times volume times gravity. And if ice is less dense than water and it's displacing the amount of volume of water that would be there, that's the buoyant force, and that's higher than the the weight force of the ice because of its low density. Whereas if you have a bowling ball, a really high density, it'll sink straight to the bottom because the volume that's being displaced of water, that weight force is a lot less than the weight force of the bowling ball. Is another way to think about it. And but one other thing to take into consideration though is there's still a buoyant force on the bowling ball. So even though that bowling ball, say out of water, just in air, where there's a lot less buoyant force, but there still is buoyant force in air, the ball would weigh a lot more in air than it would in water because the buoyant force in water is pushing up a lot more than air is. And so that's Archimedes' law, Archimedes' principle. The next one I'll be talking about is about some pump analysis stuff. If you want to, you can always control the flow of water if you want to get, like for showers, what we want is, high velocity, lots of, high velocity of water that's coming out real hot. And to do that, you need like a compressor, and that helps. And my first conceptual question is, ignoring viscous effects, an incompressible fluid flows steadily through a compressor, a narrowing radius section of pipe. The velocity blank and the pressure blank in the direction of flow. And the answer is the velocity decreases and the velocity increases and the pressure decreases in the direction of flow. And this is evident when you have the same flow rate, volumetric flow rate of water coming out of the faucet, no matter what, right? On in and out, you got the same flow rate of water, and if the cross-sectional area of the pipe is a lot larger coming in, the velocity can come in. The velocity of the water can come in a lot slower. Is going to come in a lot slower because volumetric flow rate divided by cross-sectional area is the velocity. So then, when you have a compressor, it's got a narrow radius on the out section of it, and that when you do a small area divided by, or when you divide the volumetric flow rate, the same one from the first part, by a lot smaller of an area, that'll get for a lot higher of a velocity. And if you use the Bernoulli equation, you can figure out the pressure, and that pressure is also lower due to the raise in velocity. And that's useful, yeah, like I said, for showers or for hoses and stuff. Anything where you want a high velocity of water coming out, that's the best way to do it with a compressor. The next question is some more pump analysis problem, and it's about multiple pumps. So, sometimes you can't get one really strong pump. It's more efficient to add multiple pumps. And there's two ways you can add pumps. You can add them in parallel, as seen here, and you can add them in series, as seen here. And if pumps are put in parallel, blank are additive. And if pumps are put in series, blank are additive. And the answer is the flow rates are additive if the pumps are in parallel. And that's obvious because if the flow rate's coming in and it splits up into two, half the water is going to go into one, or whatever the percentage, whatever splitter you have, the half the water is going to go into one and half the water is going to go into the other, and that'll be half the mass or the flow rate of water going into each, but on the out, they'll add back up, because there's only one out, and as you can see there in parallel. And that can be beneficial in some ways. But if the pumps are in series, you have to add the head losses of the pumps, whereas in parallel, it's not additive. It's more of a inverse relationship, kind of complicated, and that's good for minimizing head loss for parallel pumps. But for series pumps, it's the flow rate's the same through both of them, and that's just seen because it's only got one in and one out for the first pump, and the same in and same out for the next pump. But the head losses you add, and that's because once you're done with the first pump, that friction loss has already been applied, and that's still going to be applied before the second pump, and then it's going to be applied again, the new head loss. And that's another pump analysis conceptual problem. And those are our 3 problems. This is Michael Obluda. Thank you.